Hi, everyone. This is Jacob Moulton, Derek Hangeveld, and David Tobin from the Redwire Veritrek team. And we're here today to talk about what's new with the Veritrek software. So just a quick agenda of what we are going to cover in today's webinar. I see, a couple of attendees out there are our existing customers. So thank you guys for joining. But we have a handful of new interested parties as well. And so we're going to start by providing just a brief overview of what Veritrek is, what a reduced order model is, and when you can use Veritrek in your thermal analysis workflows. But we'll keep that conversation pretty short. For those of you that aren't familiar with the Veritrek, if you'd like more information, please just reach out to us directly and we'd be happy to set aside some time with you and your team where we can kind of go do a deeper dive into how Veritrek works and show you some demo videos. The primary focus for today is going to be discussion on what's new with Veritrek in this year, 2021. And we're also going to show some new customer success stories and how our customers have been using the new features that we released this year. And then at the end, we'll also give a sneak preview into what will hopefully be coming soon with our next Veritrek 4.2 release, which we're planning right now to have that released in Q1 of 2022. And so we're going to start. Derek's going to provide an overview of what Veritrek is. If you do have questions on kind of some of this high-level overview info, just please post those in the Q&A session. And we will pause right after these upfront slides if there's any questions on this high-level overview info. So Derek, I'll turn it over to you.
All right, thanks, Jacob. And hello, everybody. This is Derek Hangeveld. So let's just talk briefly about what Veritrek is for those that don't know. Essentially what it is, it's a software tool, a companion software tool to Thermal Desktop that takes your Thermal Desktop model, converts it into a reduced order form. And the reason for doing that is once we're into a reduced order form, we can run simulations very quickly, where our traditional Thermal Desktop models might take minutes to hours, in some cases days, to run a single simulation. If we run a reduced order form of that same model, we can run thousands of simulations in just a few seconds. And so Veritrek is really a three-step process. Step one, we start with our Thermal Desktop model. It can be pretty much any sort of Thermal Desktop model that you have that you're using right now. And then that's where Veritrek comes in. So we start with our Veritrek creation tool in step two. The creation tool is basically the companion tool that puts its hooks into Thermal Desktop and allows you as a user to semi-automatically convert that Thermal Desktop model into a reduced order form. At the end of step two, at the end of using the creation tool, we now have a reduced order model, or as we'll refer to as a ROM, and we want to do something with that. We want to leverage the speed of a ROM. And so we port that ROM into our Veritrek exploration tool, which allows us to do rapid analysis. And so I think here we're going to have a quick video showing what the exploration tool looks like. Here's the exploration tool in action. This was based on a NASA crew exploration tool or crew exploration vehicle simplified thermal model that we converted into a ROM and we ported it into the exploration tool. The user is going through and changing some of the inputs to that thermal model, that reduced order form of that thermal model, changing things such as radiator efficiencies. This happened to have a fluid loop in it, so there's some regenerator parameters or different working fluids. And every time the user is changing a setting, we see the results changing on the right-hand side. What we see on the right-hand side is a surface plot showing a output. In this instance, it's fluid hydraulic power versus two inputs, in this case, heat load and regenerator area per node. And really what's going on behind the scenes is that every time the user's changing an input setting, we're running 400 ROM simulations to generate the information necessary to create this response surface. You can imagine doing that in near real time is almost impossible using kind of traditional methods. Just the computational expense of running 400 simulations to get the information you need is pretty cumbersome using traditional Thermal Desktop workflows. But by converting that Thermal Desktop model into a ROM, we're able to now do those types of things. All right, Jake, we can move on. All right, so what is a ROM? In a lot of cases, reduced order modeling is based on reducing node count. That's not what we're doing here. We're actually doing intelligent sampling and then robust data fitting. So we have a very simple example. Imagine you have a thermal desktop model. You have an input factor of interest, let's say a heat load, and you want to track an output response. And let's say that's a temperature of some submodel. And so what we can do is we can run that thermal desktop model at a variety of different heat load settings. Let's say 0 all the way up to 5 watts, and we're going to track the temperature response. And we see that at 0, we get a temperature response of 10, and at 5, we get a temperature response of 60. And so we have these data points in the eyes of Veritrek. We call this training data. And what we're going to do next is we're going to fit those points that we've just created. And it looks very linear, so nice and easy to fit. We come up with this equation, y equals 10x plus 10. And so, maybe someone might come up to us and ask us, what is the output response at a heat load of, let's say, 3.5 watts? Well, we haven't sampled that point yet. We certainly could go back to the thermal model and we could put in 3.5 watts in the thermal model, and out would come our temperature response of 45. But more computational efficient is, why don't we just use the model we've just generated? It's going to be much faster. So we just put in 3.5 in for X, and out comes 45 for Y. So that's essentially what we're doing with Veritrek. We're sampling the input design space and generating this training data, and then doing a robust data fit. Although with Veritrek, we're expanding this quite a bit, as you can imagine. So we're not just dealing with one input factor, but multiple input factors. We'll see some examples later where we have ROMs built on 15 input factors. We're also dealing with basically the shape of the model, or the shape of the data that we're dealing with is really unknown ahead of time. In this example, it was very obvious it was linear, but we don't always know that with thermal models. And they're typically highly nonlinear, especially with the radiation exchange. And so we need a robust data fitting algorithm, which Veritrek provides. Veritrek also deals with multiple output responses. So not just a single output response, as we'll see later, but tens, maybe even hundreds of output responses. And then also I just want to mention that Veritrek provides the intelligent sampling. So how do we fill this design space with enough training data that we can do an effective job of making a ROM with not generating too much training data and adding additional computational expense? All right, we can move on, Jake. All right, so when can you use Veritrek? Really, the take home is pretty much throughout the design life cycle. When we first started working on Veritrek, we thought, hey, this would be great early in the design stages. We're trying to do trade studies. We want to quickly evaluate different design options. And that certainly held true. We have users using it that way. But really, we found that people are using Veritrek throughout the design life cycle, whether it's maybe you have a detailed design and you want to look at sensitivities of input factors and how they impact output responses. Later on, you might be doing a model correlation campaign. And we now have the capability of doing rapid thermal model correlation using ROMs, and which will show some success stories later. And then finally, much later in the design life cycle, when we have fieldable assets, we've had folks use Veritrek and reduced order modeling to help in those cases. An example is some of the work that we've done with NASA JPL's Mars 2020 helicopter program. All right, with that, I'm going to turn it over to Jake. We're going to kind of start to talk about kind of the new things, the new features in Veritrek.
Yeah, thanks, Derek. So we're going to start by just talking about some new features that were rolled out with Veritrek 4.0 earlier this year, in case you missed that release. Veritrek 4.0 was released in January of 2021, and that was actually a big release for us. We kind of brought along these two main features and rolled those out commercially for our users. And so those two features were a new ROM parallelization feature and a new model correlation feature. And so just wanted to kind of highlight and talk about these two new features that we rolled out earlier this year. So starting with the ROM parallelization feature, this is a new feature within the Veritrek creation tool. So the application that you use to create a reduced order model. We're well aware that, as Derek alluded to, kind of the main time investment of a user using the Veritrek software and creating a reduced order model is the time that it takes to create an accurate ROM. So the time that it takes to generate that training data that we need to create an efficient and accurate reduced order model. Since those training data runs rely on actual high fidelity thermal desktop model runs, we're actually doing runs in your thermal desktop model. And so anything that we can do to kind of reduce the time that it takes to generate that training data and create a ROM is certainly kind of at the forefront of our minds development wise. And so this new ROM parallelization feature was the first step in doing that. And it was really geared towards allowing a user to kind of split up the total number of training runs that they need to create a ROM and perform those in parallel across multiple instances of both thermal desktop and Veritrek. And so if you have multiple thermal desktop licenses, you can make use of this feature to speed up your ROM creation process. We have just a quick video here that will show how this feature works. So we're taking a look at the Veritrek creation tool right now. At this point, a user has already determined the input factors and output responses they want to use within their reduced order model. Veritrek has created these training runs for us. And what we're going to do is come over here into our ROM setup and summary tab and divide the total number of training runs into, in this example, 2 different batch files. So we're going to split up the training runs into 2 files. Once we do that, we can open up the first of 2 instances and get this ROM creation going by clicking the Start ROM Creation button. And then on a separate machine or a separate instance of Veritrek, we can open up the software in our parallel only mode, load the second of the 2 batch files, and click Start ROM Creation with this instance as well, and kind of let both of these applications run at the same time until we are finished generating our training data. Once we do that, we simply merge the split up files back together into a single reduced order model file so that we can perform our data fitting step on our full set of training data. And in that way, we kind of split up and sped up the time that it took to create our ROM. The second of the 2 features that were released with Veritrek 4.0 was our model correlation feature. And so this feature was really developed to assist thermal teams in correlating their thermal desktop models to actual test data that they measure in the lab. Typically, this model correlation process is a bit of an iterative approach where you have some symbols or inputs in your thermal desktop model that you're willing to vary. You kind of adjust those symbol values, run a single thermal desktop case, look at the output results and see how closely they measure up to the actual data that you measured from your thermal test. And you kind of keep doing this until you end up with a set of symbol values that produce outputs that are close enough to those thermocouple measurements you obtained from your test. And with Veritrek, we're just able to greatly enhance and speed up this process because we can use the power of the reduced order model to quickly compare thousands of different combinations of input parameters and let Veritrek filter out those that don't closely line up to the output data we're trying to collect. And so that's really how our model correlation feature works. It allows users to quickly find multiple viable solutions in an automated and repeatable manner. And so we have a video here that will show how this correlation analysis feature works. So this is inside of the Veritrek exploration tool. Once we set up our new correlation analysis, in this example, we're going to correlate to 2 tests at the same time. So we're going to have a cold and a hot TVAC test that we want the same symbol values for our thermal desktop model. And so what we're showing here in the upper middle portion of the screen, this is our input factor design space. So this is where the user can dictate low and high values for symbols that they're willing to vary for their model correlation approach. The area in the bottom middle is our experimental output section. And this is where a user enters in the values that they're trying to correlate to. So if you have nodes in your thermal desktop model that correlate to specific thermocouple locations from your thermal test, you can tell Veritrek what you want those node temperatures to be in this measured column here. We can also dictate a margin criteria. So we can tell Veritrek we only want to look at solutions that fall within our specified margin criteria. So in this case, we're doing plus or minus 3 degrees C for each of our temperature measurement locations. So once we enter in the values that we're trying to correlate to for the different tests we're including in our correlation approach, we're going to tell Veritrek how many combinations of input parameters we want to explore. In this case, we're going to start with 20,000. We add points to all runs. And so what Veritrek is doing is it's randomly exploring 20,000 different combinations of input parameter values within our defined design space. And it's going to filter out the solutions that don't meet our specified output and margin criteria. And what we end up with is this list or this table on the right-hand side, which tells us the viable solutions that Veritrek found within those 20,000 points that it explored. Since we're correlating to 2 thermal tests at the same time, each viable solution shows up as 2 rows, but we can see the different symbol or input parameter values in the center portion here. We can use our show hide columns feature to either kind of show or hide lots of different types of information in this table. And what I'm doing here is just showing temperature differentials between the exact values we're trying to correlate and the output results that Veritrek found. And so we'll see that kind of towards the right-hand side of this table. Now, since we specified our margin criteria being plus or minus 3 degrees C, all of these temperature differential values are going to be less than that 3 degrees C because these are viable solutions within our specified margin criteria. So this table is currently what we show in terms of correlation analysis feature outputs. We've had a number of different users kind of use this approach for their thermal desktop model correlations. And what they've been able to do is kind of right-click and save the data and results that we show within Veritrek and export those into some external kind of plotting features and capabilities, depending on how they want to visualize their results. So we've had users that have created these spider plots, and we've also had a handful that have generated histogram plots to kind of determine the most likely value for each of their inputs. And this kind of helps them determine, of the viable solutions that Veritrek shows and provides, which one is really the best solution, which one does the user want to pick and choose for their model correlation. And Derek will actually be talking about some of that user success story work specifically with the model correlation feature here in a couple of minutes. Okay, so moving on to what's new in Veritrek 4.1. So Veritrek 4.1 was released just a couple months ago, this summer of 2021. And the 2 kind of main enhancements with this latest version of Veritrek are summarized on this slide here. So one of the big things was just compatibility with the latest version of Thermal Desktop. CR Tech released Thermal Desktop 6.2, I believe in the spring of 2020, maybe the March timeframe, if I'm not mistaken. And so, we're now compatible with all versions of Thermal Desktop after version 6.0. So the latest patches of 6.2 will now work within Veritrek. The next main enhancement was the addition of a new kind of output response type that you can choose to select within the Veritrek creation tool. And this comes directly from multiple user feature requests that we've gotten. All of the development that we do here at Veritrek comes directly from feedback, comments, and feature requests that our users put into our Veritrek team. The more requests that we get for a particular feature, the higher up our development priority list it climbs. And so this maximum temperature gradient of a node group was something that lots of people asked for. And so we've been able to include that in our Veritrek 4.1 release. So how this feature works, it's pretty simple and relatively straightforward. So here in our output section, we can of course choose to track the temperature of individual nodes, registers, or entire node groups. And our previous options, we could choose to track the minimum, mean, and maximum temperature of our node group across a transient thermal analysis run. And we now have the ability to choose max temperature gradient for our selected node groups as well. Okay, so now we're going to get into some of our new customer success stories and kind of show how customers have been using Veritrek over this last calendar year. And a couple of them have been using these new features that we just highlighted and discussed. So we're going to start by just providing an overview of how a thermal group at NASA Goddard used Veritrek to help improve the thermal design for one of their thermal models involved with the EXCLAIM project. And so this is a NASA Goddard experiment for cryogenic large aperture intensity mapping. It's essentially a cryogenic balloon-borne instrument that's going to survey star formation history over very large cosmological timescales. They were able to use Veritrek to do two main things with their thermal desktop model and thermal design. The first was kind of a small design optimization effort. Veritrek helped them determine the optimal placement of one of their components based on temperature requirements. And then they also used Veritrek to perform a temperature sensitivity study. Now, one of the interesting things and one of the exciting things for us about this new customer success story is the number of input factors that they used for this particular reduced order model. You'll see some of those specs on the right-hand side of the screen. They ended up including 33 different input factors in their reduced order model. And that is the most that we've seen from a user model to date. The thermal desktop of theirs, the runtime to perform a single thermal desktop run was on the order of like 15 to 20 minutes. And so typically, the more input factors that you want to include in your reduced order model, the more training data runs you're going to need in order to produce an accurate ROM. And so that can be, a limiting factor in some cases, but we're very excited and happy to kind of point to this use case to say, 33 input factors, you can have 33 different symbols that you can include in your reduced order model and use Veritrek to kind of explore the design space with that large number of input factors. This particular ROM, it took about 3.5 days of automated runtime to kind of churn through their 340 training runs and produce an accurate reduced order model. A lot of that was done kind of over a weekend. So if you set up your reduced order model in the creation tool, maybe on a Friday afternoon, kind of click go and or use our new ROM parallelization feature, you can just let Veritrek kind of automatically generate that training data over a weekend when your thermal desktop licenses aren't being used. You can certainly pause and resume your ROM creation as well. But typically, we advise folks to leverage the weekends and kind of the off time where thermal desktop licenses aren't being used to generate their reduced order. So speaking a little bit about how specifically they used Veritrek, for their design optimization effort, they used Veritrek's surface plot analysis feature. So that's shown on the left-hand side. We can see they were looking at the X translation and Y translation. So that simply refers to the location of one of their components. And they wanted to find the optimal placement based on motor control and temperature requirements. And so they used Veritrek's 3D response surface plotting feature to kind of help determine that optimal component placement. And then in the middle portion, they used Veritrek's screening analysis feature to do a temperature sensitivity of multiple kind of scientific instruments that were on board this EXCLAIM model. And that's really what the screening analysis feature was designed for, was to perform these temperature sensitivity studies. And so you can see along the x-axis are certain input parameters of interest, and we're looking at how each input parameter impacts our output responsive interest on the y-axis. This uses Monte Carlo methods to perform this sensitivity study. The larger the bar graph, the more of an impact on average changing that particular input's value is going to have on our output response. And so you can really use this to identify those thermal design drivers and kind of focus your design and optimization efforts on those parameters that do have the biggest impact on your output response of interest. Okay, at this point, I'm going to turn it back over to Derek to go through a couple more of our new customer success stories.
Yeah, thanks, Jacob. So this first one we're going to talk about here is the Mars 2020 helicopter program. We were pretty fortunate to be a part of that team, several years ago during the design stages. And so we used Veritrek back then to help with optimization of the helicopter design. And then this slide really talks more about the mission ops attributes of Veritrek. So here, JPL was using Veritrek to develop a reduced order model of their flight unit that would help them with mission planning. So one of the challenges with the Mars 2020 helicopter is that there's a very tight window to do mission planning. And they really would like to run through a variety of different scenarios, thermal scenarios, to ensure that they're going to get the helicopter warm enough for flight. And so that's how they were using it. And so we ended up building a ROM with 8 input factors, 19 output responses. We had a ton of calendar time to throw training runs at it. So we ended up just running this thing like Jake had mentioned earlier, just ran this in the background when we weren't using licenses. So we ended up with 3,600 training runs. And, because of that, we certainly ended up with a really nice, accurate ROM. You can see some of those test results in the bottom right. And so, this is a ROM that's currently being used on that helicopter. Jake, we can go to the next slide. This slide and the next one really talks more about our Veritrek model correlation feature. The first one here is Ball Aerospace. They used our model correlation feature to help with thermal model correlation of a cryo instrument. We can see a rendering in the upper right. Had multiple components to it. What they ended up doing was taking that and splitting that into 3 separate thermal models. They're essentially thermally decoupled from one another and creating 3 separate reduced order models. Then they use those ROMs to generate multiple ROM iterations to find viable correlation solutions. In fact, they ended up using 20,000 ROM iterations to produce, roughly 4,500 viable solutions that met their correlation requirements across 10 different test cases. So, we have multiple test cases, multiple output responses that we're trying to correlate to multiple input factors. And by using Veritrek, we can do that relatively quickly. They found out of those 4,500 solutions, we use a group factor performance to kind of whittle out or rank some of the better performing solutions. And then of those, Ball, they ended up looking a little bit more closely at those and ended up finding some viable solution or a viable solution that worked really well. It turns out that they ended up, this only took a couple of days to do this ROM model correlation, whereas using traditional approaches, they thought it might take, in the order of weeks. So it's an order of magnitude reduction in the time required to do model correlation. All right, Jake, we can go to the next slide. The next one is some work out of NASA Goddard on their LRALPH instrument. You can see a rendering of that in the upper right. What's really interesting about this, well, there's a couple things here. One is that they had quite a few input factors. So 15 input factors, 70 output responses. Took them about a day of time to generate the reduced order model. The model ran fairly quickly, so they could do that pretty quickly. And what they did is, kind of in the traditional Veritrek model correlation approach, they have this model correlation ROM. They generate thousands of viable candidates, and then they sift through that. But what NASA Goddard ended up doing is then taking that information. Again, Veritrek provides not just a single set of input values that are suitable for model correlation, but a collection of input values. And they ended up using or producing these distributions, which we can see in the bottom middle of these input factors. And then they started to talk about, well, some of these distributions look different than others. The one on the bottom left there, it's a deterministic distribution where there's really only one really predominant setting of an input factor that met correlation requirements, and that would be, hey, this is where you need to set that input factor. In this case, 0.04, right? It was pretty dominant there on that histogram. But on the right-hand side there, we have an indeterministic variable. Maybe as this particular input factor variable it gets higher, maybe it trends towards more of the viable solutions. So maybe we want to generally move the dial a little bit higher for that one. But it helps us pinpoint or more accurately find these input factor settings that are going to meet our correlation requirements. So really interesting work here. And both of these works from Ball and NASA Goddard, there are presentations and companion papers. The companion paper for the Ball work. So if you're interested in that, just reach out and I can get you some of that, some of those details. All right, we can move to the next slide, Jake. Okay, so we covered some of the success stories. You know, we have a variety of users using our current features, but where are we going from here? You know, I think Jake had mentioned multiple times that, you know, the features that we developed are really customer driven. So we're listening to folks like you, trying to identify what are you guys looking for in Veritrek. And one of those capabilities is uncertainty quantification. And so this is something that we're actively working on, actively developing. You can see an example of that here in this image. Essentially what we're doing is leveraging the speed of reduced order models to provide uncertainty quantification. And essentially what we're doing in the middle here, we have a set of input factors, and each input factor, the user provides a range from a low value to a high value. And then what Veritrek does is it's going to go through those ranges of input factors and pick and go through thousands of different combinations. And from those, it's then going to plot the distribution of an output response of interest on the right-hand side. In this case, we actually have two runs set up, a high power case and a low power case, and that's why we have two of these distributions, one in blue and one in red. And so what we see here is that under the input ranges that we have set, this is the distribution of output responses that we would expect. So let's just look at the high power case, the one in red. We can see that it's generally centered around, let's say, a temperature of roughly 300 Kelvin or so, maybe a little below, but it can reach temperatures up to 370 Kelvin. And not very likely, but it certainly could based on this distribution. So it really provides a lot more insight in our thermal design. You know, should we be designing things? Should we be concerned that we're going to get out to 370 Kelvin? Well, it's not very likely. It could happen. But now you're going to play the probability game. So, you know, this is something that we're actively developing. I would offer that if you're interested in this, we do have a beta version of this feature. We'd be happy to get this in your hands. You can play around with it. You know, it's pretty quick and easy to kind of get some of these results. We'd love to hear your feedback to help us kind of finish off the development. So if you are interested, reach out to myself or Jake or David, and we'd be happy to set that up for you. All right, Jake, next slide. Yeah, so here I'm going to turn it back to Jake. That's what we had for today. You know, I really appreciate everybody's attendance. And Jake, take it from here.
Yep, thanks, Derek. So yeah, this is, you know, all the content that we had to share with you guys today. Certainly, if you're interested in, you know, investigating Veritrek further, for those of you that aren't as familiar with what we're doing here, certainly reach out to me. We can, you know, get a conference call set up with you and your team. We can provide you with a free trial of Veritrek at no cost to you. And for those of you out there that are interested in the uncertainty quantification feature that Derek was just talking about, we do have that available in a beta version right now if you're interested in kind of playing around with that and seeing what it can do for you in your thermal desktop models. As Derek mentioned, we're always you know, listening to what customers and users say, you know, things they like about the software or new features, things they don't like. That is really what drives our development. So anyone that's interested in either a free trial or a beta version of the uncertainty quantification feature, please feel free to reach out to myself, Derek, or David directly, and we can get you set up with that. So thanks everybody for joining today.